I will be talking about discrete valuations and discrete valuation rings. It is a part of commutative algebra and number theory. It's used in both, and in fact, for the geometric part, discrete valuation rings are just ring of gems of functions on smooth one-dimensional complex manifolds. But for number theory, this is things like what is called local rings. I would probably spend some time on that part of math because it's very natural from what we started. Okay, so now let's go for the definition. So the definition is related to periodic norms. I will explain what it is. And yeah, suppose you have K as a field. Then you have a multiplicative map, multiplicative in the following sense, from K without 0 to Z is a valuation if nu is homomorphism, so nu of xy is nu of x plus nu of y. This is the first condition. It's not complicated. But there is a second one which is slightly less elementary. Nu of x plus y is bigger or equal than nu minimum nu of x and nu of y. So let me give an example. Example includes periodic valuation, but it makes sense for any factorial ring. So I have example. Yeah, before I do that, let me also valuation ring. A nu minus 1 of 0 inside K is a ring. Why it is a ring? Well, first it is multiplicably closed by this, sorry, not of 0, but of positive, positive nu minus 1 of non-negative numbers. Sorry. Is a ring. This is a ring for the following reason. First, if you multiply two things which are non-negative, their sum is nu of their product is sum of their valuations, and it is non-negative. And second, if you have two things which are non-negative, then the nu valuation of their sum is bigger or equal to the minimum of their valuations. So if x and y are in this set, then their sum also belongs to this set because it's nu of it is non-negative. So this ring is called valuation ring for this valuation. So nu minus 1 of z non-negative is called the evaluation. Ring of nu. Now example. Suppose that R is a factorial ring. This means that every element of this ring is a product of primes and fix a prime. Prime P, and let R be a product of prime Pi power Ki multiplied by P power N. So that Pi are not equal to P. This is a prime decomposition of a an element x. Then nu of x is equal to n. This is called nu p. This is called periodic valuation. So if you have, for instance, well, if you have x is equal to a quotient by b, p power n, a and b, p are coprime, then nu of x is n. I just rewrote this in different terms.
What does n mean first?
Sorry?
What does n mean? The first? No, the first one.
Yeah, here. This is n. Okay, so why it is evaluation? First, you have x of nu of xy is clearly nu of x times nu of y. This is because x and y is something coprime to p times p some power. Then their product is, if you first you multiply the coprime to p parts, they remain coprime to p, and then you multiply powers of p. The exponents are added. So this is why we have, sorry, plus here. The evaluation is multiplicative. Now if you have nu of x plus y, and suppose that nu of x is n, nu of y is n plus d, this means that x is a quotient by b, p power n, and y is a1 quotient by b1, p power n plus d. Then x plus y is a b1 plus p power n plus a1b p power n plus d divided by b1 bb1, right? This is how you add the fractions. But then b and b1 are coprime, b1 are coprime with p. And this means that a b1 p power n plus a1b p power n plus d. The valuation of this thing is the same as valuation of x plus y, because the denominator is coprime with p. And then this is equal to nu of p power n, a plus b, ab1 plus a1b p power d. Okay. Now this is coprime with p. If d is, we assume that d is non-zero, is non-negative. If d is equal 0, this can be divisible by p. This is, a priori, this can be divisible by p, but this, this is an element in R, so its valuation is at least 0, maybe bigger. But if d is non-zero, then this is definitely coprime with p, so nu of this thing, Pn times is equal n, where d is bigger than 0, or bigger or equal than n to n, where d is equal to 0. Because in the first case, this is coprime with p, and the second case, we don't know. It can be coprime or can be whatever. Okay, but anyway, it's integer, so the only it contributes to something non-negative, and n can contribute to something negative or positive depending on the sign of n. But in any case, we obtain that nu of x plus y is bigger or equal than mean nu of x, nu of y. Is it clear? I'm sure you have seen this for periodic valuations. This is very standard when you define periodic numbers. And then the corresponding valuation ring is A divided by B, where A, P, D, where A, B, P are coprime, and D non-negative. So this means that you invert all elements of R which are not divisible by P. We had already this. So in other words, this valuation ring is localization of R in this ideal. This is a prime ideal generated by P, and we invert all elements which don't belong to this ideal. Make clear? This is standard valuation. So, well, we shall discuss it more, but, well, we shall discuss it more. But if you did periodic numbers, you have seen it a lot. Okay, so what we are now want to characterize the rings which are obtained this way. So definition. In fact, we will never have any examples except that I gave here, and there's a reason for that. They pretty much don't exist. And this is what we shall see now. Okay, the definition R is discrete valuation ring. If R has no z divisors. This is the fraction field. Is given by nu minus 1 of z non-negative, where nu is a discrete valuation. I didn't say it, I should. This is surjective. Of course, if it's not surjective, then it maps this ring to some ideal in Z, and this ideal you can normalize by dividing by some n, and it will be surjective. So it doesn't really matter. Every subgroup of Z is cyclic. So you can always assume that this is surjective. Okay. Was I clear with this? So let's list some properties. So proposition 1. The funny thing that here I characterize discrete valuation ring by that it is local, Noetherian, integrally closed, all ideals are principal, and the crude dimension is 1. In fact, this also converse is also true. So pretty much every of these conditions, like all ideals are principal, integrally closed, are equivalent, and they're all equivalent to discrete relation, you will see. But let's first start with the properties. One, sometimes people abbreviate discrete relation rings to DVR. Discrete relation ring. Every DVR is a local Noetherian. What else? Integrally closed. All ideals are principal. Cruel dimension is 1. By the way, what does it mean that cruel dimension is 1 for a local ring? It's a very nice condition because it's much better than for other rings. So you have 0 sits inside your maximal ideal, right? It's a local ring. And this sits in R. Okay, this is a chain of length 2. So it is the maximal length for cruel dimension 1. For any other chain, if you have some other ideal, Q, then it contains 0, it is contained in R. So it should be intermediate. But cruel dimension prohibits, it's dimension 1, there is no second ideal. So cruel dimension 1, so nota bene, cruel dimension 1 plus local is equivalent to only 2 prime ideals exist in MR. Okay, so this is really strong condition. Okay. So let's prove it. So proof. Step 1. If you have X such that so you have a okay. So this is a DVR. So it is nu minus 1 of the non-negative, where nu is a map from, say, K to Z. Surjective. It's our evaluation, K without 0. So what is K of 0? You can actually define it will be infinity. This is because what is actually nu of something where you have prime P? This is the maximum number which you can use to, the divisibility number. You divide your element by P and you take the maximal power, but since 0 is divisible by any power of P, this means that nu you can, if you want to extend nu to 0, you will obtain infinity, and this would actually satisfy these properties as well. I'm not doing it, but it is sometimes people do this. Okay, so we take X inside K. This is our ring. And this R is the discrete relation ring we started from. And nu of X is 0, then X in R is invertible. This is because nu of X minus 1 minus nu of X. So if you want, if it is 0, it is clearly invertible and vice versa. Okay, so what is maximal ideal? Maximal ideal is an ideal such that all elements which don't belong to this maximal ideal of a local ring. So I remind you that if you have P inside R, and R is local, and this is maximal, P is maximal, this is equivalent to all x in R without P being invertible. Indeed. Well, if the ideal is maximal, and then all elements not in this ideal are invertible. Yeah. Anyway, so this is what we need to show is that sorry?
Why if norm is 0, then the element, the corresponding element is...
Because if norm is, the relation is 0 of x, relation is 0 for x minus 1. So both x and x minus 1 belong to this discrete relational ring. Then it is invertible. Because both x and x minus 1 are in this ring. Okay, so if all elements not in this maximal ideal are invertible, then there's no other maximal ideal except this one, because if there's an ideal which is not contained in this one, it's not an ideal. There's no ideals which can contain invertible elements. So this is why this implies that it is local. Conversely, if it is local, then, of course, for all elements which don't belong to this maximal ideal, this element is invertible or belongs to some other maximal ideal, but we have only one maximal ideal. So all elements which don't belong to this maximal ideal are invertible. Good. Now we have our ideal, a new minus 1 of z positive. It's an ideal in R. Let's denote it by P. So if x is not if x belongs to R without P, this is equivalent to x being invertible. Because this is precisely this is also equivalent to nu of x being 0. Okay, then this is local. Then P is local. Is maximal, so R is local. And P is this maximal ideal. Okay. Oh, here it is R, sorry. I changed A to R everywhere except on the first slide. Sorry about this. Okay. Now we take a generator. So we know that this, by definition, this is surjective. So this means that we have, there exists, so this was step 2. Take P in R such that nu of P is 1. Then for each x in R, such that nu of x is n, nu of P minus n x is 0. So let's call this u. This is invertible element, and x is u p power n, which also belongs to, yeah. So this means that every element is p n times invertible, and this is a factorial ring. That's just unique prime. Then our ring R, which is A on slides, R is factorial with a unique prime, which is okay. I mean, why do you need more primes than one? It's even better if you have just one prime. And this implies, in particular, that all ideals are principal. Because, okay, take an ideal, take the smallest power of p which is contained in this ideal, and it generates it by this argument. Because all elements which have bigger or equal relation to that element are divisible by p. So it is principal ideal ring. It is local. Now, cruel dimension is 1 because there's just one prime ideal. I mean, we just have listed all ideals. They're all power of the maximal ideal. So they cannot be prime except one, which is maximal. Okay, so what else? Yeah, it is integrally closed because it's factorial. So it remains only to prove that it is Noetherian, and that's it. So so step 3. Noetherian means that you have if you have an increasing sequence of ideals, it has to terminate. But then all our ideals are powers of p. So you have p power k1 contained in p power k2, contained in p power k3, and so on. And we can assume they're all different. So this means that k1 is strictly bigger than k2, strictly bigger than so on, strictly bigger than kn, and so on. And this has to terminate because it's all positive integer numbers. Has to terminate. And this implies that R is Noetherian. Was that clear? Good. Okay, so there's lots of ways to characterize. I will write that later because I'm not going to prove. I just wanted to show you that this is a really convenient notion because it has lots of equivalent characterization. So if you have a local field of cruel dimension 1, then it's discrete relation ring, if only if it is integrally closed, if and only the maximal ideals principal. This is the tangent, what is called Zariski tangent space, or cotangent space. It should be one-dimensional. Every non-zero ideal is a power of m, which is, most of these properties we already had, except this one. Sorry?
This is a cotangent.
Yeah, cotangent. Yeah, thanks. Okay, so this I will prove later. So the most difficult part now is to prove that if a ring is integrally closed, local, Noetherian, and has cruel dimension 1, it is discrete relation ring. The difficulty is that you need all of these things. You need Noetherianity, you need the integrally closedness, and it's sort of hard to cram all these conditions into one notion. So this is why the proof is hard. And the shortcut is using this fractional ideals, which is probably, historically, this is probably the way how ideals appeared. So ideals for Kummer, who invented the term, were like special kind of numbers which can be used to have factoriality in rings which are not factorial. This is ideal numbers which still can preserve a bit of factoriality. And so this was the, of course, if you speak of numbers, it's only natural to speak of fractional numbers, and this is how you work with the these fractional ideals. These are a bit like ideals, but not in the ring, but it's in its fractional field. So definition. Suppose you have I inside, so you have ring R, ring. You have K of R, it's field of fractions. So today we won't have any rings which have zero divisors. So all rings will be what is called integral domains. You have I inside K of R, R model. So R acts on this by multiplication on this ring. So it makes sense to speak of R models. And I is called fractional ideal. If there exists A inside R such that AI sits inside R. Okay. I'm not sure if it looks like a natural notion, but there is a very simple explanation why it is natural, which requires neutrality. Of course, in commutative algebra, pretty much everything requires neutrality, but somehow people are very shy in this discrete valuation ring to business to assume neutrality. They don't do this assumption until the last possible moment. So usually they use this definition instead of assume neutrality. But with this, neutrality is much easier. So you have I inside K of R, R model, and assume that R is Noetherian. Then I is a fractional ideal. If and only if I is finitely generated. So proof is very easy. Okay, suppose that I is finitely generated. So we have I is generated by some set of AI divided by BI. These are fractions. It's generated as R model. So this means that if you multiply multiply all elements of I by product of BI. It belongs to R. So if it's finitely generated, then it is fractional ideal, right? Immediately. Conversely, if AI sits inside R, then AI, this is an ideal. It's a submodel in R. Is an ideal, and ideals in Noetherian rings are finitely generated. But as a model, this is isomorphic to I. Because it's multiplication by A, it's an isomorphism of submodels. Okay, so we proved this pretty small result. Now let's do something with these fractional ideals. The idea is that you can add them, you can multiply them, you can do almost everything what you can, what you would expect from numbers. And this multiplication and addition satisfies the standard axioms. Of course, What is false is that you don't have 0. It's not a group under addition. So if you have I1, I2, so I1 plus I2 is all sums of x inside I1, y inside I2. This is clearly also a fractional ideal. You just multiply this thing by something which takes I1 to R and something which takes I2 to R, then this would be also moved to R. Another thing is I1, I2. It's all products. For the same reason, this is also a fractional ideal. Of course, you can use non-trianity for that as well, because they have finitely many generators for I1 and I2. For some, and our product also has finitely many generators, but it's easier not without non-trianity. And of course, you would have associativity. You would have things like I times I1 plus I2 belongs to I1 plus I2. So this is really similar to numbers in that sense. OK, so now we're interested in intersections. It's an operation which you, of course, don't have for numbers, but it still works for the intersections. So claim you have I1, I2 in Kf are fractional ideals. Then I1, oh, sorry. Of course, I feel very stupid, sorry. It should be non-empty. No, sorry, it should be in definition. In definition, it should be not. They forgot to tell. So, non-empty. I.
Non-zero.
Yeah, non-zero. It was in the slides, but I forgot to tell it. So this I should be non-zero. Otherwise, for 0, this condition becomes trivial, and there is nothing to prove now, and we want to prove something. So this is fractional ideals. Then I1 intersected with I2 is also fractional ideal. Of course, there is nothing to prove except that it is non-zero, because since I1 is mapped to R by multiplication by some element, then the intersection also has this property. So the only thing we need to show that it is non-empty. Then it is, of course, a fractional ideal. OK. Yeah, so proof. You have I, whatever, I1, belongs to R, but it also belongs to I1, because A is an R. Well, if it's not an R, you just multiply it by denominators so that it becomes an R. And this implies that I1 intersected with R is non-zero. Now you have this ideal. You multiply I1 intersected with I2 by A. This is equal to I1 let's do it like in slides. You have a, so we already know that I intersected with R is non-zero, so take AI in this intersection. II intersect with R. Then you have A1, A2. It sits in R times II. Right? So it sits in R intersected with I1. It also sits in R intersected, multiplied by I1. It sits in R multiplied by I2. But this is obviously I1, and this is obviously I2. So this product sits in I1 and I2. Okay, not that it's hard, but something should be proven. Am I clear? Okay, one more observation. So we can do this, even try to invert fractional ideals, and in a sense it's invertible. Again, this is something that in a very strange sense. So fractional ideals are a bit like numbers, but not quite. This is why Kummer called them ideal numbers. So let's denote, so claim. You have I inside K of R fractional ideal. And define R of I is a set of all x inside K of R such that xi sits in I. This is actually a ring. And then you define I minus 1. It's a set of all x in K of R such that x times I minus times I belongs to R. So this is clearly submodules, R submodules in this field. I'm going to show that this is also fractional ideal. For that, I would now give a construction which encompasses both of these two constructions. So you have I1 and I2 fractional ideals. And you define J, which is the set of all x in the fraction field, x in K of R, such that xi1 sits in I2. So when I1 is I2 is I, this is this, and J is R of I, and when I1 is I and I2 is R, J is I minus 1. So if we prove that J is fractional ideal, then all other two are also. Then J R of I and I minus 1 are fractional ideals. Okay.
Why do you have to take from K of R? Because on the slides you have this.
It's a misprint? No, where do I have in R?
I R minus 1.
Yeah, it's a misprint, sorry. Thanks for pointing this out. It's definitely a misprint. Thanks. Yeah, we actually use that it is not in R. And to some points, it's really important. Thanks for noticing this. I should correct this. Okay, so proof. So the proof is, first we have to prove that J is non-empty. And then we have to prove that it has this property of, is mapped to R after multiplication by some element in R. Okay, so what we have is that there exist A and B, so it's step one. We have A and B inside R without 0, such that AI1 belongs to R and B belongs to I2 intersected with R. This is non-empty as we proved, and this is A exists because of, by the definition of fractional ideal. Then we have to multiply these two guys, and suddenly they become, they belong to J. Op. Yeah, I think here I inverted something. Should be probably, let's check. Something is wrong in the slides. I think it just numbers are missing, but okay, so we want AB times I1. So we know that I1 belongs to R, so this belongs to B R, right? And B belongs to I2. So this belongs to I2. This means that AB belongs to J. And here I found another misprint. You see it's I2, I1, should be inverted. Am I clear? Okay, so this is why it is non-empty. Now we need to show that it is, yeah, so now we do the opposite sort of. So step 2, we take C inside intersection of R with I1. Intersected with R, and D such that D of I2 belongs to R. This is again D, C and D are non-zero elements, so there is R without 0. This is sort of, I take A and B and invert the order. So you take B equals C and A equal D, I think. Maybe, no, you can't, sorry. Okay, now we have J, X inside J. I want to prove that CD times X is in R. What is CD times X? And then, of course, I want to prove, this is not proven, I want to prove it, the CD X in R. If I prove that J is a fractional ideal, right? Because X is arbitrary. Okay, so C, we know that J, X maps I1 to I2. And C is in I1, so Cx belongs to I2. And D, Cx belongs to R. This means that CD of J belongs to R. And we have finished the proof. Sorry?
Why CX is the element of I2?
Cx, because x maps x times I1 belongs to I2, right? And C belongs to I1.
Yeah, okay.
So this product belongs to I2. Thanks for the question. Okay. Another chain of very similar observation which we need is this climb one, which tells us that R of I for any fractional ideal I contains R. Obviously, this contains I minus 1. And moreover, if I was an ideal inside R, then I minus 1 contains R. So this really behaves like inversion. Of course, if you do I and then I minus 1, it's not an involution. It might happen that, for instance, I minus 1 is R. This happens sometimes. So you can't expect this analogy between numbers and ideals and fractional ideals to be perfect. Okay, so proof. You have R of I contains R because I is an ideal. I mean, I is R model. Now, R contains I minus 1. It's by definition of I minus 1, because for each x in I minus 1, xi belongs to R. Then this belongs to R. Okay, this is the first claim. And the second claim, if you have I inside R, so I just finished proving that we have this first chain of embeddings, which is almost trivial. Now this is the second embedding. We have, if I sits in R, then for each x inside R, we have xi sits in R. And this implies that x belongs to I minus 1. Because what is I minus 1? It's all elements of K of R such that all x such that xi belongs to R. Okay, I will use this claim shortly. Questions? So this was like preliminary business, which is pretty much trivial. Now we have a theorem which is not very trivial. In fact, the proof which is in T. MacDonald uses pretty much all book of T. MacDonald. So I took this proof from a number theory book. Okay. And the theorem says that if you have a discrete ring which is local, integrally closed, and has curl dimension 1, and Noetherian, it is a discrete relation ring. It's called proposition 2. And it is hard. So if you have R, local, Noetherian, curl dimension of R is 1, and integrally closed, then R is a discrete relation ring. Okay, you can think about that, and we have temos intervalo para 5 minutos. Okay. So I'm going to prove this proposition 2, and in fact the converse is already proven. It's proposition 1. So we needed only one direction. Okay, so the first step, step 1, is the only step where we use that it is integrally closed. Okay, so we're interested in R of I, where I is a fractional ideal. R of I, it's a submodel in home over R from I to I, right? But then it is finally generated. Finally generated. And it also contains R of I. It sits in the fraction field, and it contains R. So it is R of I sits between R and K of R, and it's finally generated, so it has to be equal R of I is equal to R because R is integrally closed. This is the only step where we use integral closedness.
This
Yeah?
element of home because of using just about x going to Rx, and this is element of home, just multiplication by the element of
R of I belongs to K of R by definition. It's
what's home?
yeah, but then it's a map from I to I.
Multiplication.
Yeah, yeah. There could be some other elements, but it sits there. It's inside this homomorphism space, homomorphism model. On the other hand, it is also belongs to this fraction field. So it is two different interpretations of the same algebra. So generally speaking, it's not even clear why this homomorphism ring is commutative. It's not necessarily commutative, but since it belongs to K of R, the R of I is commutative.
But why it belongs to K of R?
Sorry?
Why it belongs to K?
By definition. So R of I is all elements of K of R which map I to itself.
Ah, okay.
It's how we defined it. So it's a fractional model inside the ring of fractions. Again, step 2 is something we have discussed already. We have 0 sits inside maximal ideal. It's a maximal chain of prime ideals. And every prime ideal is also sits between 0 and m, and since the Krull dimension is 1, this means that 0 and m are all prime ideals. Something we already have seen. Okay. Now I'm going to show that I'm going to use the neutrality. I'm going to show that this is non-trivial. Step 3. We need to show that m minus 1 is not equal, it's contained, but it's not equal to R. It's obviously clear when m is prime is principal ideal, because when it is principal ideal, then this m minus 1 is generated by p minus 1, where p is generator of m. And we're going to show eventually that m is a principal ideal. So this is a natural thing to show. Okay, so first observation is that if you have a principal ideal, so if A is inside R, principal, and R is obviously non-invertible, then this ideal minus 1 is generated by A minus 1. So more or less by definition. So if something is multiplied by A and it becomes integer, this means that it is, if you have this A minus 1 times A, so X, because X belongs to A minus 1, if you non-leave, then XA belongs to R. This is a definition of A minus 1. So this means that X belongs to a fractional ideal generated by A minus 1. Okay. So at least you have one fractional model which has this property that its inverse is not equal to itself. Because obviously not elements in R are invertible, it has dimension 1. Okay, so we define set S inside, so it's a set of ideals, I in R, such that I minus 1, it strictly contains R. It's not equal to R. And I have a partial order on this S by inclusion. So take J inside S maximal. It exists because now we use Noetherianity. Every increasing chain of ideals terminates. So it contains some, so S contains a maximum. So if we prove that J is prime, we immediately obtain that J is equal to M, and M minus 1 strictly contains R. So this is what we need to show. We need to show that J is prime. Go on. Okay, so let's prove it. Yeah, I guess we can erase this. This is step 4 now. It's the most non-intuitive proof in the whole step in the whole proof, but it's fortunately short. So you have X and Y inside R without J. And we can assume by absurd, we are going to prove that its product is not in J, so absurd, assume that XY belongs to J. And then you have Z. Take Z inside J minus 1 without R. So we know that J minus 1 is strictly bigger than R. This is because J is chosen in S. It's a maximal element in S. Now we take zy multiplied by x r plus j. So this belongs to R. Why? Well, xy belongs to j. Zj belongs to R. And zxyj belongs to zj, which also belongs to R. Zj belongs to R. Zxyr belongs to j. The xyr belongs to j. Zj belongs to R. So this is y. Okay. And then we have an ideal J1, which is xr plus j. It is not an S. It's bigger. Well, it can be, yeah. And it is okay. Then this means that J1 minus 1 is equal to R. And this implies that Zyj1 in R. And we have Zyj1 in R because Zyj1 is in R. This we have. This implies that Zy belongs to R. Because this means that Zy belongs to J minus 1, J1 minus 1. But J1 minus 1 is R, is our ring. S is this set of all ideals here, set of all ideals I in R such that I minus 1 strictly contains R. And this guy is bigger. It can't strictly contain R. So it is equal to R, fine. R is fine. Then because R minus 1 is R, obviously. Or it is it satisfies J1 minus 1 of is equal to R. And then Zy J1 belongs to R, then Zy sits in R. Because J1 minus 1 is R. Okay. Now we have another ideal, which is yr plus j. So z times yr plus j belongs to R again. Because zj belongs to R, and zyr also belongs to R, as we have seen here. Okay, and this implies that, but z is not in R. This implies that yr plus j minus 1 strictly contains R, because it contains z. And this is a contradiction. We found a bigger ideal which also has this property which doesn't belong to S. Can be. Should I repeat? This argument is bizarre. it's entirely different from what we have in ITM McDonald, but ITM McDonald took, their argument is equally non-intuitive, but it takes content of all of the book of ITM McDonald preceding chapters, which we actually had. So it uses the primary decomposition and some other things. I think this is easier. And it's sort of more conceptual because it uses these fractional ideals, which are fun. Okay, so I will start step 4 from the beginning, right?
No, the part
With J1?
yeah.
Or with this ideal? So in the end, we obtain that Zy is an R, right? Okay. Now we have Z multiplied by this ideal is belong to R. Because Zy belongs to R and J belongs to R. Yeah. Look at this ideal. It y r plus j minus 1 contains z. Because of that. Then this ideal is not equal to r. This fractional ideal is not equal to r. But it can't happen because j is a maximal element in S. No bigger ideal than j can satisfy this property. And this implies that y actually belongs to j. This is a contradiction. Because we assume that x and y don't belong to j. Okay. I can repeat again. It's really non-intuitive. For me, it took some time to figure out what goes on. Okay. Now we have step 5. So we're interested in finding what is m minus 1. And we have this claim 1 here, which tells us that m minus 1 contains R, and it contains m minus 1. This is, again, multiplication of fractional ideals. And then if we have m minus 1 is equal to m, this implies that m minus 1 belongs to R because R of m belongs to R. This is step 1. If you remember, we used that R of any fractional ideal is R. It follows from integral closeness. But this contradicts to step 4. So this can't happen. And since this can't happen, this implies that m minus 1 this is an ideal in R, which is or R itself. One of two things. But it can't be an ideal because it's smaller than m. So it has to be R. It's strictly smaller than m by this. Then it is equal to R. Okay, this was step 5. We have 7 steps. It's probably the biggest proof in the whole course. So now we have to use notoriety again. It's Krull lemma. If you remember, it follows from Nakayama that intersection of all powers of any ideal in an Noetherian rings is 0. This is because if you multiply, this intersection by this ideal, it will be this equal to itself. So step 6 intersection of m power I is equal 0 from I equal 1 to infinity. This is powers of our maximal ideal. And this applies that for each x. For each x, there exists k such that x belongs to m power k without m power k plus 1. You have this filtration by this ideal, and it is proper. And I choose P. I fix P inside m without m squared. In a moment, we shall see that it is a generator of the maximal ideal. So to see that, first we notice that Pm sits in R. Pm minus 1 sits in R. M minus 1 contains, it contains R. Which direction? Sorry. Yeah, it contains R. It's contained in R, so it sits in R. This is because of that. So we know that m minus 1 is R, so if you take a part of m, it will be an element, and it will sit in R. And then I want to say that it's actually, it's equal to R. Otherwise, a priori, it could be slightly bigger, slightly smaller. So we take P, m minus 1, m. Multiply these two guys will be R. So this is equal to P. This we know. And then we can multiply it by m minus 1 again. So P, m minus 1, so P doesn't belong to m squared. P doesn't belong to m squared. So if you write here m squared, this would be it's obviously it's contained in m minus 1 m. Well, it's contained in P. Sorry. Okay, so we have P doesn't belong to m squared, and m minus 1 m minus 1 m squared is equal to m. This means that P m minus 1 doesn't belong to m because P m minus 1 m doesn't belong, which is equal to P r, because m minus 1 m is r, doesn't belong to m squared. So P m minus 1 doesn't belong to m. But then it's an ideal it's a submodel. So P m minus 1 is a submodel in R, which doesn't belong to m. M is the only maximal ideal. So anything which doesn't contain m is in fact R. So this implies that P m minus 1 is R. Good. Yeah, so this in turn, if we multiply both sides by m, and we use m minus 1 is equal r, we'll obtain that p is r multiplied by m, which is m. I just multiply both sides of this equation by m. And this implies that m is a principal ideal. So obtained we obtained that m. Okay, now step 7, and that's it. Now everything is very easy. So you have for each x in m power k without m power k plus 1, x is equal to p power k so it's better to say p power minus k times x belongs to r without m. I just take this model and I multiply it by m minus k. And this becomes m, and this becomes r. Just we use m minus 1 is equal r, and we do it k times. Okay, so this is invertible. Is invertible. And then R is factorial ring. And now if you have any x inside k of R has form p power n times u, where u in R is invertible. Well, it is true for any elements in R by this argument, and then it's true for any fractions for clear reasons. And to define nu of x as n. In that assumptions. Then x inside R, if and only if x is p power d times u, where d is non-negative and u invertible. And this happens if and only if nu of x is non-negative. So the proof is finished. Was I clear?
I absolutely lost the steps.
Since when? Since this?
No, step 6.
Yeah, so step 6 is done as follows. So you have p outside, you choose fixed p inside m without m squared. Now you have m minus 1, m squared is equal to m. And this means that p
Why m minus 1 times m squared is equal to?
because m minus 1, m is equal to r. And you use associativity of multiplication of fractional ideals. And then you take p multiplied by m minus 1. So p belongs to m, and this therefore this belongs to R. But it cannot belong to M, because if it does, then if P M minus 1 belongs to M, then P belongs, I multiply both sides by M minus 1 and I obtain P belongs to M square, which contradicts our assumption on P. So this means that P M minus 1, that P M minus 1 is equal to R. Indeed, this is a submodel which contains M, and it is bigger than M. It properly contains M. And anything between M and R is equal to R, unless it is M. Now we'll multiply both sides by M and obtain that P is equal to M. Every time we use this assumption obtained in step 5, that M minus 1 is R, which is crucial. Okay, so this gives us that M is principal ideal. Now, first we notice that if you have some other element, you can always choose it in M power k without M power k plus 1, if it's an element in R. And then it's decomposed into a product of some power of p and something invertible. And the same is true for any element in k of R, so and then R of R. So R is factorial with the only prime element, P. And then you define, using this prime element, you define the, well already had it. If you have a factorial ring, you immediately have a p-adic valuation, which I wrote here. And then what is element in R? Element belongs to R if it is p, some power p times invertible. This is precisely that nu of this element is non-negative. That's it. So this we obtain that this R is the situation ring. Was I clear? Good, thanks. Okay. There's an important observation which I could probably done earlier, but it is really important. That not all discrete valuation rings are born equal. There are some rings which are entirely different from other rings. So look, let's define the residue field. So definition, you have M inside R, the maximal ideal. You have R over M is a field, which is called residue field. Sometimes K is embedded into R as a section. So you have this embedding, and the projection is an isomorphism. So the typical example is you take K of T, and you localize it in the ideal T. This means that you invert all polynomials which are non-zero in 0. And the quotient is K. And of course, K sits here as constant polynomials. So this gives you a section. Okay, there's another example. In fact, if you are careful, you can prove for characteristic 0 that this is pretty much always happens. It takes some work, but for characteristic P, this is definitely not true. And there is an example. Again, you have Z localized in P. So the integers localized in P. This means that it's a ring. It's a ring of all fractions, A divided by B, with B, P, coprime. So you invert all functions, all integers which don't belong to the ideal P. And this ring contains this ideal generated by P. This is a maximal ideal. So the quotient Z by quotient by P is obviously Z by P. It's finite field. You can embed finite field in characteristic 0, whatever. So this projection is definitely different. And this plays important role in number theory because there are things called functional fields where you have this section, and there are things called number fields where you don't. And I have a trivial claim, which I'm going to use next slide. So claim 2, which says that if R is DVR and you have K is residue field, R by M. Okay, the important thing that the direct sum M K by M K plus 1, this quotient, is in fact a model over this ring. Because if you multiply something by M, an element from here multiplied by M, it arrives to M power K minus 1. It is projected, so this is K vector space. And its dimension of Mk over Mk plus 1 is 1. Sorry?
Why dimension?
Here's the proof. So proof, if you have a generator so let's define, to consider generator. This is discrete evaluation ring, so it has a generator of maximal ideal. So P is M. So maximal ideal is generated by P. And consider the map multiplication by P power D. So it was D here, D and D, as in slides. L P power D of X is P power D times X. And then LPD defines an isomorphism from R to M power D. And this isomorphism maps M power M to M power D plus 1. So this implies that R quotient by M is equal to M power D quotient by M power D plus 1. This isomorphism is provided by this multiplicative map because of these two isomorphisms. Clear? And this is by definition has rank 1 over K because it's K. Okay. Was that clear? Now I can show you this huge chain of equivalences. We're almost out of time, and I have to write it down. Should I now stop and repeat it from the start next time, or should I finish now and write it down? What is your preference? No? Next time. Oh, good. So we shall proceed. Next time we shall proceed from this place. Thank you very much. Muito obrigado. Eu termino.